Hi, welcome to, sorry, okay, let me do that again. 3, 2, 1. Hi, we're HawkSat, and welcome to our presentation. I'm Olivia.
Damon.
I'm Logan.
And I'm Alexa. In order to guide ourselves in the process of building our CubeSat, we set requirements for ourselves. In terms of performance, our CubeSat will use the camera to capture images of ocean plastics, which will then be analyzed by our ground station and hopefully identified with 80% accuracy, while we also attempt to conserve and budget our power. Our survival requirement is for our CubeSat to be durable and to survive the stress of launch and orbit for around 6 months. In terms of interface, our CubeSat will communicate efficiently with the ground station with a minimum amount of data being sent back and forth. Finally, for workmanship, we will use materials with low outgassing and resistance to erosion and other stressors of the space environment. This is our concept of operations diagram that walks through the process of our CubeSat's functions. Before launch, we will test all of our systems, then we will launch. Once the CubeSat is in orbit, we will test the systems again, then the CubeSat can begin its work. The ADCS will map the location of the CubeSat over the Earth. The Raspberry Pi camera will take photos and compile the data. Then it will run the error correction code, save the data to the SD card, and compress the data before downlinking it to the ground station. Once the ground station receives and decompresses the data, it will map the location and analyze the photos. Finally, the ground station will uplink new information and new functions to the CubeSat so that it can begin another cycle.
And here we have the systems level block diagram. We can see that there are 6 subsystems on the satellite, the structure subsystem containing a large amount of parts securing everything together, the Raspberry Pi serving both as the computer and communications device, the NOR camera as the science subsystem, the IMU as the ADCS subsystem, and the solar panel and power pack as the power subsystem. So basically, every subsystem is integrated with the Raspberry Pi. And now on the right, on the ground station, there is communications and a command and data handling subsystem.
Next up, here is an overview of the software architecture, including several different systems. We'll be looking more in depth at the various parts of it over the next couple of slides. Throughout, things in red boxes will continue to run each orbit as a loop. First up, the on-satellite software. In the ADCS system, we have initial recording of data during the first orbit based off of the measured magnetic field and its correlation with Earth's magnetic field, initial deployment position, acceleration, and orientation data, which is all sent down to the ground station to generate a function predicting orbital location, and then sent back up so it can be checked on the satellite, which reduces the amount of link budget used, as well as the amount of memory used, and provides an easy means of determining where the satellite is. The science subsystem first takes a couple of calibration photos, as well as calculating the number of photos that need to be taken to get the required amount of overlap. After that, the science section takes photos when the CubeSat is over the ocean and highlights non-cloud regions that are a different color from the ocean, as most plastics should not be ocean colored, and then sends that to the ground station, allowing more data to be gathered without straining the link budget or memory budget as much. In addition, we have a power system that checks how much power is in the battery, as well as a command and data handling system to use error correcting code and protect our data against SEUs and reduce corruption from noise during downlink, as well as compressing the data. Next, we have the ground station systems. We have a similar communication system to reduce noise and allow for data compression, as well as a small power system to make sure that the battery isn't strangely draining too much. For the ADCS system, we have a collection of best fit function mapping to get our orbital function, starting off with correlating the magnetic data to predict an orbit, then adding in any rule using the gyroscope, then combining those two and checking it with the acceleration data. In addition, we have also a small loop at the bottom to allow for any possible necessary changes to the orbital function. Finally, we have the heart of the matter, the science subsystem. The first step here is to overlay the satellite images with the location data from our orbital function, and then project that onto actual positions on planet Earth, so we have a nice map of the data. After that, we adjust for atmospheric effects and use a YOLO V3 AI, since it's fast and relatively efficient, to remove clouds. Once that's done, for the actual identification of the plastic, we use 3 different AIs, a faster RCNN AI, an SSD AI, and a YOLO v3 AI in order to detect plastic and cross-correlate the results for higher accuracy. Next, yet another YOLO v3 AI, that's my favorite if you can't tell, classifies the type of plastic and assigns a mapping number to it, which is important for some of the later steps. The data is also stored in a database for raw data storage purposes, but is also passed on to the next step where the plastic classification is combined with the predicted path of plastic from ocean currents data to identify how the plastic moves from one observation to the next, and a function is mapped to that. From that function, the path of the plastic can be backtracked to a potential location of origin. Once we have this path, it can be uploaded to a publicly available repo, then displayed in a dynamic map form for ease of observation, possibly using a GIS integration.
So here we have a general CAD model of our CubeSat. And so there's the battery, there's the Raspberry Pi, the Nord camera, and the IMU. And the parts that are not pictured would be the aluminum rails and the acrylic plates and the solar panel.
To start off with our link budget, we need to determine how many photos we are taking. Using simple geometry and ignoring refraction as data at the edge of our visibility is not going to get thrown away anyways, we can determine how much of Earth's radius we can observe at any time. That is, if we approximate the Earth as a sphere. Using that and the plan from the software architecture, such that we will have 420 photos looking at every spot on the planet, we can calculate that we are going to take 20,805 photos. But since each photo will be averaged for both storage and transmission with 4 other photos, we are effectively dealing with 5,200 photos. Estimating the size of each photo with the margin of error after compression as a PNG, we are generating 41,600 kilobytes of data per orbit. Then, after assuming our orbit is circular and it is at 400 kilometers, we can determine the speed of motion and use the parameters of our communications system to calculate the Shannon limit. Multiplying those together and accounting for the fact that our system is not likely to operate at the ideal link capacity, we get the total amount of data we can send per orbit and confirm that we are not only sending less data and images than our link budget can sustain. So we have extra space to send our power data and function data. Since we are sending slightly different data during the initial orbit for calibration, we are just doing a sanity check to make sure that we are not exceeding the link budget here. We can estimate that each IMU measurement outputs 9 integers, and assuming 32-bit integers, each IMU measurement is worth 288 bits. We can then calculate the total amount of data per orbit from the IMU based on the frequency of measurement, and then add the data for our calibration photos and confirm that we are not only still under the limit, but we also have an even bigger margin, which is great in case we need any code corrections once we realize that the CubeSat is in space. So for a power budget, we have 3 major components that I would like to cover for today. So first of all, we have a battery, which will provide our power, our voltage source. And then we also have a solar panel, which charges very slowly. As you can see over here, when our power input is going to be 0.503 watts. Our Raspberry Pi, our IMU, and our camera are going to be linked together since they are all connected to the Raspberry Pi, and that will consume between 3.8 and 5.5 watts. But as these calculations do not account for wire resistance, we have also included a 9% margin for the greatest power consumed by the Raspberry Pi, which will be 5.5 watts times 1.09, which is going to be equal to 6 watts. So over here, we have a mathematical model, which is a very simple linear model, and it has 3 parts to it. So firstly, we have our y-intercept, so that's going to be our 37, and that will account for the amount of the voltage source from the power from our battery. And we also have our 0.503, which will account for the amount of power that our solar panel can supply. And lastly, we have our -6, which will account for the amount of power that our Raspberry Pi and the other components combined will draw from our power source. But as you can see over here, our CubeSat barely reaches 7 hours full of charge, and we can only run it for about 7 hours. We will bring this up to Piazza and our mentor, but as of now, we can't figure out why this is so. But we can assure the audience that we are working on it, and we will hopefully get something that is closer to 6 months.
So next up, we have the mass budget. So we're building a 1U CubeSat, so that's 10 centimeters by 10 centimeters by 10 centimeters, which means our maximum allowable mass limit is 1.33 kilograms. So it falls under the, and our CubeSat falls under this limit at 1.13 kilograms. Looking through the list, we can see that this is mostly self-explanatory, but for the one important note is that in a lot of these estimates are for the worst case scenario for our team. So this is effectively our estimate of the maximum amount of mass of that thing that we could possibly be using in our CubeSat. Next up, we have the data budget. The data budget we can determine using the amount of photos calculated from the link budget and a similar estimate for their size. In order to compress the photo data, we can use the fact that most of the photo regions looking at the same area to greatly reduce the space by only marking the differences in each region, even accounting for reasonable uncertainty in this process, as well as another estimate of the maximum size of our orbital function and a margin of error for any additional data that needs to be sent up or down. We get that we have 6 gigabytes of space to create our initial code in, which should be plenty of space and gets us under the 16 gigabyte limit of our SD card.
This is the assembly, integration, and testing. So we begin with the assembly of the structure. Then we will integrate the Raspberry Pi, followed by the camera, the power pack, and solar panel, and finally the IMU. Then we will perform a stress test, an outgassing and vacuum test, and an interfacing test, then a plastics recognition test, and finally a test for single event upsets. These are our testing measures in more detail. First, to test durability, we will simulate vibration using a shake plate to make sure that our CubeSat will survive the stress of launch. To test outgassing and the effects of vacuum conditions, we will leave our CubeSat in as near a vacuum as possible for an extended period of time and then measure mass loss and check for any damage. To test interfacing, we will attempt to send data between our CubeSat and ground station from over 1 mile away. To test plastics recognition, we will attempt to photograph plastics in the East River from the Queensboro Bridge, which is over 300 feet high. To test for single event upsets, we will take our CubeSat to Grand Central Station, which is mostly made of granite, so it has high levels of ionizing radiation, or we will use the radioactive material in a smoke detector to induce bit flips and see if our error correction code can catch them.
Thank you for watching.
Thank you.
Thank you.